In this lecture, we're going to go over the polytropic process relationships for ideal gases. If we recall, a polytropic process is PV to the N is equal to a constant. And in between two states, we have P1 V1 to the N is equal to P2 V2 to the N, or P2 over P1 is equal to V1 over V2 to the N. N can have any value between negative and positive infinity. If N is equal to 0, we have an isobaric or constant pressure process. If N is equal to plus or minus infinity, we have a constant volume process. For a polytropic process, our work is equal to the integral of PdV, which is P2 V2 minus P1 V1. Again, N cannot equal 1. If N equals 1, we get that our work is equal to P1 V1 times the natural log of V2 over V1. So our above relationship applies for any gas, but we can make further simplifications for ideal gases. If I relate two states of the ideal gas law, I have T2 over T1 is equal to P2 over P2 V2 over P1 V1, which is V1 over V2 to the N times V2 over V1, which is equal to V1 over V2 to the N minus 1. Or if you do it in pressure in terms of volume, you can get T2 over T1 is equal to P2 over P1 to the N minus 1 over N. Our work, which is P2 V2 minus P1 V1 over 1 minus N, is MR T2 minus T1 over 1 minus N. Again, I use the fact that PV equals MRT. For N equal, this is for N not equal to 1. For N equals to 1, we have our work, which is equal to P1 V1 times the natural log of V2 over V1, which is equal to MRT times the natural log of V2 over V1. And for an ideal gas, N equals 1 is an isothermal process. We're going to look at a quick example. We have air undergoing a polytropic compression in a piston cylinder assembly from 1 atm and 70 degrees Fahrenheit to 5 atm. We're going to employ the ideal gas model with a constant specific heat ratio K, and we're going to determine the work for a value of N equals 1.3 and N equals K. So our work per unit mass is equal to R T2 minus T1 over 1 minus N, but we need T2. How can I find T2? Well, I'm going to do an energy balance, which shows me that my heat transfer is equal to my change in internal energy plus my work per unit mass. Since actually insert another edit, we need T2. Well, I'm going to use my polytropic relations to tell me that T2 is equal to T1 times P2 over P1 to the N minus 1 over N. So I have 530 degrees Rankine times 5 over 1 bar ATM to the 1.3 minus 1 over 1.3. So T2 is 768 degrees Rankine. So my work per unit mass is equal to 1.986 BTUs per pound mole degree Rankine, divided by 28.29 pounds per pound mole times 768 minus 530 divided by 1 minus 1.3. So I get my work to be minus 54.39 BTUs per pound. To find my heat transfer, since there's no kinetic or potential energy changes, I'm going to use my energy balance and get that my heat transfer is equal to my change in internal energy plus my work. Since the problem says to assume constant specific heat ratio, I'm going to have that my heat transfer is equal to my work plus CV times T2 minus T1. So I'm going to get my minus 54.39 BTUs per pound plus 0.717 BTUs per pound degree Rankine. I chose that value from table A20E. 768 minus 530 is minus 13.69 BTUs per pound. If N is equal to K, my heat transfer per unit mass is going to be equal to R T2 minus T1 over 1 minus K, that's my work, plus CV times T2 minus T1. And if we recall, CV is equal to R times K minus 1. So I'm actually going to get R T2 minus T1 for 1 minus K plus R T2 minus T1 over K minus 1. So when I get my heat transfer per unit mass is equal to 0. And that is an important concept. For N equals K is an adiabatic process. So that's actually it for chapter 3. In our next lecture, we will start chapter 4, which brings in the concept of open systems or control volumes, whereas everything we have done up until this point has been on a closed system.